In the early 1900s, Harvard astronomer and personal hero Henrietta Swan Leavitt was tasked with studying Cepheid variable stars. Belonging to a broader class of objects known as pulsating variables, Cepheids are a type of star that expand and contract repeatedly over time, causing their brightness to vary in a predictable manner. I study auroral Lyrae stars, a dimmer but more common type of pulsating variable with many of the same properties. Auroral Lyrae are of broad scientific interest, but my current project is primarily concerned with using them as distance indicators. Astrophysics research, for the most part, can't be conducted in a traditional laboratory setting, and as such, it's important that we develop clever and robust methods for determining distances to extragalactic sources. So imagine for a moment, for example, a 100-watt light bulb. If I hold it up really close in front of your face, it will appear very bright. It might even hurt your eyes a little bit. Whereas if I were to hold it from a mile away, it would be so dim you may not see it at all. You already understand that there's a relationship between the inherent brightness of the bulb, 100 watts, how bright you observe it to be, and your distance to it. The same is true for any celestial source for which we know its intrinsic brightness. We call these sources standard candles. So in her research, Leavitt discovered a relationship between how quickly a Cepheid pulsates, which we can observe from Earth, and its average inherent brightness. This relationship, colloquially known as Leavitt's law, has been adapted and refined to the broader class of pulsating variable sources, including auroral Lyrae, allowing us to use them as standard candles. The catch, however, is that Leavitt's law needs to be recalibrated depending on what filter or color of light you're observing in. Such a calibration already exists for the Hubble Space Telescope, and with funding from NASA and the Space Telescope Science Institute, I have developed a first-of-its-kind calibration to the newer James Webb Space Telescope. For this, I make use of observations of nearby galaxies like WLM, where we really focus on looking at galaxies for which we have observations in both Hubble and JWST, so we can link our new calibration to the existing work. It's important to obtain such a calibration, as James Webb boasts a much larger primary mirror than Hubble ever did. And as such, it's able to make out individual stars with sufficient clarity in increasingly distant galaxies. Auroral Lyrae standard candles are a very robust distance indicator, and as such, it's necessary for us to use them as far out into the universe as possible. Doing so helps us to better refine our understandings of things like the size and distribution of the universe, understandings upon which the entire field of cosmology is founded. Thank you.